Hi, my name is Aaron Holman, and I'm a physics PhD student at Columbia University working with Sebastian. Today I'll be talking about our progress towards a programmable Strontium Tweezer array and what we hope to do with such a platform. Atomic tweezer arrays have recently blossomed as a platform for exploring many disparate areas in physics, ranging from metrology, quantum optics, quantum computing, and quantum simulation. Our atomic species of choice, Strontium, offers many advantages in pursuing these goals. Strontium's previous role in pushing clock science demonstrates its robustness in control techniques and meaningful atomic transitions. Strontium also has both readily accessible bosonic and fermionic isotopes. While we are currently focusing on bosonic strontium-88, there's plenty of other physics to be explored with fermionic strontium-87. Looking at its Rydberg properties, as an alkaline Earth atom, when strontium is excited to a Rydberg state, the atom remains trapped by the tweezers. Clearly, strontium has many advantages that can be implemented in a tweezer array. Our experimental setup is particularly compact, as well as an ultra-high vacuum environment. Within this vacuum, we employ a novel strontium source that is loaded into a 3D magneto-optical trap where our magic tweezers trap and rearrange atoms. Our array pattern will be produced by a metasurface to create arbitrary non-periodic geometries. First, our strontium source. We heat a dispenser that directly loads the atoms into a transverse 2D MOP. This greatly reduces the footprint and cost compared to the conventional setup for similar AMO experiments of an effusive oven and Siemens loader. We successfully were able to observe the 2D MOT and steer it into the downstream glass chamber, where the 3D MOT is currently being constructed. We saw a flux of just under 1 million atoms per second with an average velocity of 50 meters per second, far below the capture velocity. If you'd like to learn more, Minho Quan, a postdoctoral researcher on the project, will be presenting in depth on our source this DAMOP. Next up is our tweezer light. We are using the magic wavelength of 520 nanometers for the 1SO to 3P1 transition. Magic in this case means the polarizability for both states is the same, reducing the effects of fluctuations between traps. Using an acousto-optical deflector in tandem with a computer arbitrary waveform generator, we have been able to generate homogeneous periodic arrays. Our closest spacing between traps has been less than a micron, with a 168 by 168 array. As you can see, the traps remain individually resolvable. Even with just an AOD generating the array, we still have simple arrangement schemes involving turning off and adjusting columns or rows frequencies. Finally, metasurfaces are an exciting new development we bring to atomic array experiments. A metasurface is comprised of meta-atoms, small Lego-like blocks that change how light interferes in space. Alongside our collaborator, Professor Nanfeng Yu, we are able to create arbitrary holographic traps with spacing as low as 350 nanometers. These surfaces also have increased resolution compared to conventional spatial light modulators. Our preliminary results show a single beam creating a triangular lattice, a pattern inaccessible to just an AOD-generated array. The AOD still remains useful, however, in performing more complex rearrangement, acting as an atom relocator to any trap location. With our platform, there are a few areas we hope to explore. Subradiance, the quantum optics phenomenon where decay is suppressed, has only recently been weakly demonstrated. However, with our metasurfaces allowing us spacings of half our primary transition of interest, 689 nanometers, we believe we'll be able to show subradiance in a strongly interacting regime. Strontium also offers a readily accessible transition of 3 microns, one that would display deep subradiance. In particular, protocols involving subradiance would help create a long-lived quantum memory. Unlike many quantum systems, where larger systems are more disordered, the more atoms we have, the stronger the suppression. Simulations of a 1D chain and 2D ring show that not only could we suppress the decay of a single excitation, but it also might be possible to deterministically release the said excitation by breaking the ring. Quantum simulation and computation are also an area of interest for our platform, where one looks to encode information onto the quantum state of the system. Briefly mentioned before, this is usually done with Rydberg states, where the principal quantum number is large. Neutral atoms in general have an advantage as they are weakly interacting, and only strongly interacting when we want them to be. The Rydberg blockade is one of the available interactions for our system. This works very well in simulating condensed matter type problems that can be encoded onto an Ising Hamiltonian, or graph problems such as the maximum independent set. On the digital side of things, neutral atoms also have access to gate-based computation. In particular, certain gates such as the C0 gate are native to the platform, such that it takes fewer operations than other leading quantum computation platforms to implement. Another advantage is because of the tunability of the interaction, atoms are able to talk to one another from a large range, removing the need for qubit transfer gates such as the swap gate. In summary, our setup introduces novel ideas in every part of the atomic array experiment and looks to serve as a robust platform for many years to come. I'd like to thank all of my colleagues who contributed to the project, and I'm excited to see what we can achieve. Thank you for listening, and please feel free to reach out for any clarification or questions you may have. Thank you.